So in the previous class we have discussed a lot about the interaction picture. So today we shall repeat the discussion on the interaction picture. So for an exact Hamiltonian or an exact H naught, suppose you can describe the system in two different pictures. Okay. So H naught is time independent basically. This H naught, the original Hamiltonian is time independent, where H naught is equal to E square by twice n plus Vx. So this Vx, the unperturbed potential, is time independent potential. So thus you have two different pictures to describe the system. One is Schrodinger picture, one is Schrodinger picture. In Schrodinger picture, the wave function is time dependent. That means the wave function has the time evolution, psi s. So this is suppose psi s. And the operators are static. In Schrodinger representation or in Schrodinger picture, the operator are static. So this is 0. Okay. So in Schrodinger picture, the wave function is time dependent and the operator is static. On the other hand, for Heisenberg picture, the wave function, suppose psi is static. Psi h is static. But the operator OH is time dependent. Operators in Heisenberg picture are time dependent, but the wave function, suppose this is psi h, is static. And you have the relation between these two representation or these two picture as psi s t is equal to some time dependent unitary operator ut of psi h 0. So this is the relation between Heisenberg picture wave function and the Schrodinger picture wave function. And generally this time dependent unitary operator is e to the power minus I h naught e by h cap. Okay. So similarly, the conjugate relation, that means for bra, so this is the k wave function. For bra, you have psi s t is equal to psi h 0 of u dagger t. Okay. And here u dagger is the Hermitian conjugate. U dagger is the Hermitian conjugate of u. It should be e to the power I h naught e by h cap. Okay. So h is Hermitian basically. So it's not the original Hamiltonian. H is Hermitian. So this is the correspondence between Schrodinger picture and Heisenberg picture. Okay. But you can write in the general way. I am taking the time reference as t equal to 0. Thus the Heisenberg picture wave function I am taking at t equal to 0. But you can take any particular time interval or any particular time instant t naught. That means suppose you may have written suppose in psi s t is equal to e to the power minus I h naught t minus t naught by h cut of psi h t naught. So this is more general. This is more general representation, because in the previous case I have taken the Heisenberg wave function to be static at t equal to 0. Okay, but here I am taking any arbitrary time instant which is fixed, of course. There the Heisenberg representation is fixed, and there is the correspondence. And here the unitary operator u would be function of t and t naught in that way. So this is the correspondence between Schrodinger picture and Heisenberg picture, two well-known picture used in the conventional quantum mechanics. Okay. Now we should obtain the relation between operators also. These are the correspondence between wave functions. That means the Kates and the Braggs. Okay. But you have to find the correspondence between the operator also. So let's start from the expectation value of the Schrodinger operator. The expectation value of Schrodinger operator, taking the first case, that means we have fixed ourselves at t equal to 0. So this one should be psi s t os 0 phi s t. And this is the expectation value, the well-known definition of expectation value or the ensemble average of any operator. Now you can put the correspondence of Schrodinger picture wave function and the Heisenberg picture wave function. So that's why you can write this is psi h naught u dagger of t, then os of naught u of t, then psi h of 0. And you know the expectation value should be invariant in any representation, in any picture. Okay. Whether you take the Schrodinger picture or you take the Heisenberg picture, the expectation value of any operator should be same, because this is the real parameter or a real measurable quantity which should be invariant in all representation. So that's why you can write this is psi h, sorry, OHT, expectation value of the Heisenberg operator. And also I am taking it in different equation. So this is suppose OH expectation value. That means the expectation value in the Heisenberg picture, that is psi is 0 of OH of T and psi is 0. Now you can make the comparison between these two expectation values, this one and this one, and effectively it will yield OH T is equal to U dagger T OS 0 OS 0 and U T. So now we have the correspondence between the Heisenberg operator, which is time dependent operator, and the Schrodinger operator, which is static operator. Okay, so this is the correspondence between Schrodinger and Heisenberg. So these are very familiar to all of you, both these picture in quantum mechanics. Okay. Now the problem arises whenever the Hamiltonian is time dependent. That means suppose now you have a system uh, initially the system had the Hamiltonian is not. The initial system is not. So for initial system, you can use either the Heisenberg picture or the Schrodinger picture, whatever you can prefer. But if you can perturb the system by some time-dependent perturbing Hamiltonian, let's suppose this is h of t. Okay, h of t is equal to h naught plus h prime of t. This h prime of t is a time-dependent perturbing Hamiltonian. For example, in the previous class we have made some examples, like you have a atomic system, a hydrogen atomic system, and you allow some electromagnetic wave passing through the atom. An electromagnetic wave is essentially consisted of electric field and magnetic field, both are harmonically dependent on time. E is equal to E naught e to the power I omega t. B equal to B naught e to the power I omega t. Thus, these time-dependent fields can make some time-dependent perturbing or time-dependent perturbation or time-dependent disturbance to the system, and the whole Hamiltonian of the system will now be converted into time-dependent Hamiltonian. Okay. So in general way, you can also introduce some strength of the perturbation. Suppose is h of lambda t, which is h naught plus lambda of h prime t. This lambda ranging from 0 to 1, and it determines the strength of the perturbation. Okay. With analogy with the previous time independent perturbation case, this lambda is identical. It will denote the strength of the perturbation. Okay, so you can just control the perturbation. You can just regulate the perturbation. How much strength it will provide to the system. So h of lambda t is equal to h naught plus lambda of h prime t. And the important thing is this h prime of lambda t will make the whole Hamiltonian to be time dependent, such that in this case uh, you can apply you can apply neither Schrodinger picture, neither Schrodinger nor the Heisenberg picture, because uh, essentially this h of t, it will yield p square by twice m. Okay, sorry, p square by twice m plus some phi of xt. Okay. And whenever you want to find the solution for Schrodinger equation, like ht of psi equals to ih ka del psi by del t, this is the original Schrodinger equation. You cannot make the separation of variable in the formal way. Okay. For a time independent Hamiltonian, you can make the separation of variable of the wave function and you can find the formal solution. And after that, you can use any of the two picture, either Schrodinger picture or the Heisenberg picture. But in this case, whenever the whole Hamiltonian is time dependent, Hamiltonian depends on time, that means this potential term is time dependent. In this case, you can make the separation of variable of the wave function. So thus you can apply the previous two. So in this case we can use the interaction picture, which is very important in this scenario. Interaction picture. So in interaction picture, suppose you have psi h psi h of 0 is a static one, and you can find psi h t is equal to ut of psi h 0. This was the previous description of quantum mechanics. Whenever the Hamiltonian was h naught, that means time independent. But if you use ht, time dependent Hamiltonian, then the corresponding wave function, which was previously regarded in Heisenberg picture to be static, this will not be time independent. So due to the time dependence in the potential, due to the time dependence in the perturbing Hamiltonian, the psi h will not be time independent, rather we will find some time dependence here. We will find time dependence. So to distinguish it from the normal Heisenberg picture, I am denoting it as a psi tilde. So you can write it as psi h because it's not the normal Heisenberg picture. In normal Heisenberg picture, okay, mind it, in normal Heisenberg picture, the wave function should be time independent, like that. Yeah, the wave function is time independent. Okay. But whenever you have the Hamiltonian to be time dependent, ht, the corresponding wave function analogous to the Heisenberg wave function is itself time dependent. So that is not the Heisenberg wave function, but analogous to Heisenberg wave function, but it is not the Heisenberg wave function. And from here you can find the Schrodinger picture analog psi t. It is identically of ut of psi tilde t. This is the interaction picture. Okay, and here it is not the conventional Schrodinger picture, so you can drop this s. So what does it mean? This means whenever the Hamiltonian is itself time dependent, ht is equal to h naught plus h prime t. Suppose I am using the lambda for convenience, lambda t is equal to that. Due to this time dependence, you have already the time dependence in Heisenberg analogous wave function, and after that you have the time evolution of psi t, which is u of t of psi t, and this ut is the unitary operator. This ut is unitary operator itself. Okay, and this ut, by approximation, you have to take this ut to be to the power minus I h naught t by h car, not h t by h car. So this is the approximation. Okay, this ut is approximation. So you have the complete wave function now. You have the complete wave function psi t, which is time dependent wave function. And this time dependent wave function has two types of time dependence. Mind it, two types of time dependence. One is due to the Schrodinger picture. Which is ut e to the power minus I h naught t by h car, and another is due to the time dependent potential psi tilde. So it is due to the time evolution, which is general from the Schrodinger picture, u of psi t is equal to that, and this is the analogous of Heisenberg picture. But the difference is that in normal Heisenberg picture, this should be static with time. But here, due to time dependence, the Heisenberg analogous wave function is itself time dependent. So both Schrodinger and Heisenberg picture is completely embedded or partially embedded in the wave function. Okay, this wave function has two types of time dependence. One is due to the Schrodinger analog, and another is due to Heisenberg analog. So thus this representation or thus this picture is called the interaction picture or interaction picture. Interaction. Okay. So now we have the complete representation of a wave function in the interaction picture, like that. Okay. Okay. So now you can put this wave function in the Schrodinger equation, and you have the Schrodinger equation I h cut del psi by del t is equal to so this is our complete Schrodinger equation. Okay. Now you can put this one. You can put the value of psi t in the Schrodinger equation. So at first you have to make the derivative of this term, and derivative of this term you will yield minus I h naught by h into this one. So I h cut minus I h naught by h of ut of psi tilde t, okay, plus I h cut u of t del psi tilde by del t, okay, equals to h naught plus lambda h prime of t of ut of psi tilde. Okay. Now look at carefully. This is h cut and h cut. I and minus I should be 1. So this portion and this portion will be cancelled out from both left hand and right hand side. Okay. Okay. So this was I h cut. From the both sides. So now the rest of the equation is sorry, this one should not be here because I h cut I am taking common. So this I h cut is outside the bracket. So now you have I h cut of u del psi tilde by del t equals to lambda h prime lambda of h prime t u of t and phi tilde of. Now you can operate both the anti-unitary, that means the Hermitian conjugate of the unitary operator. I h cut u dagger u should be 1 for unitary operator. So you have del psi tilde by del t equals to lambda u dagger h prime of t u of psi tilde. Okay. So what is that? This is already the operator with time dependence h prime of t But this h prime of t, it's due to the dependence is the time dependent perturbation. And after that evolution, u dagger u, which will yield the Heisenberg analog. Okay, Heisenberg analog the of the Schrodinger. So you can write this is h lambda of h prime tilde, okay, h prime tilde of, so I h cut. This is suppose psi tilde dot. You can write I h cut psi tilde dot equals to lambda of h prime tilde psi tilde. So this is the working Schrodinger equation in interaction picture. Okay, so this is the corresponding Schrodinger equation you can use in the interaction. Whenever the Hamiltonian will be time dependent, that means the Hamiltonian has some time independent part which is unperturbed portion of the Hamiltonian, and the perturbing part which is time dependent part. So you can write the Schrodinger equation or the effective Schrodinger equation in terms of only the perturbing part, and in this case you can write the Schrodinger equation in this fashion. Okay. So this is the Schrodinger picture. This is the very well known interaction picture. Now in further calculation, we have to apply this interaction picture for analyzing some systems. Okay. So further, you can simplify this Schrodinger equation. You can simplify this Schrodinger equation using the orthonormal spectrum. Okay. So how can you develop the method for orthonormal basis of the unperturbed system? So look at carefully the development. Okay. So suppose you have the unperturbed Hamiltonian of H is not, and it has the spectrum N naught, which is N naught, N naught, which is the unperturbed spectrum N naught. And in the time independent case, we have to denote it as naught, N naught, because after the perturbation, after the application of perturbation, N naught will go to N. That means the original spectrum was changed there. But in the time dependent case, there will be no effect on the spectrum. Okay, the individual energy levels will not be changed. Actually, what change will be found to the system? The whole system will make a transition from initial state to the final state. So thus, we need not use this not we need not use this not convention, because before the perturbation and after the perturbation there will be no change in the spectrum. So you can use only N to denote the spectrum. Okay. So you need not write not here also. Okay. And this spectrum are suppose orthonormal. That means Mn is equal to Kronecker delta. Okay. Now, whenever you have h of lambda t, which is equal to h naught plus lambda of h prime t, then there will be no change in the spectrum. Spectrum will be same. Okay, but we have to analyze the whole wave function of the system, not the individual spectrum. Okay, that means suppose you have a hydrogen atomic energy level. This is 1, this is 2, this is 3, and due to the time dependent perturbation, there will be no change in the individual energy levels. Rather, the whole wave function of the system of the whole wave function will make a transition from one state to another. So that means we have to emphasize on the whole system rather than the individual energy level. So in interaction picture, you have psi tilde of t. Okay, psi tilde of t. So psi tilde will be the linear superposition of the linear superposition of the individual spectrum. So this is suppose uh, n equal to from 1 to infinity. This is suppose a n of n. So psi tilde t, it will be a n of n. Now n is time independent. Of course, a n is stationary state. This n, the original spectrum, are time independent. That means these are stationary states. Okay. So now, how can you infer this time dependence within the whole potential, whole wave function? n is time independent. The spectrum are time independent, but the whole system will be time dependent due to the perturbation. So thus, you have to infer this ANT, that means the probability coefficient. Those probability coefficient AN should be time dependent. That means, in a complete sense, the wave function of the whole system can be written in that way. Psi tilde of t is equal to that. And from here, you have psi t is equal to u of t over n equals to 1 from infinity of ant of n. Right? So, you can write summation over n from 1 to infinity an of t n e to the power minus I en t by h car. Whenever this ut will be operated over n, it will yield e to the power minus en t by h car, because h naught of n, it will yield en of n. So e to the power minus I h naught t by h car over n will yield e to the power minus I en t by h car of n. Following the Cayley-Hamiltonian theorem in matrix. In matrix method, you have the Cayley-Hamiltonian theorem, and it will dictate this situation. So thus, psi of t is equal to that. Okay. So psi of t is equal to this. Now, in terms of the orthonormal unperturbed spectrum, you can write the whole wave function of the system in that case. Clear? So you can write the wave function in that. What is the difference between normal, that means in Schrodinger picture, and interaction picture? In Schrodinger picture, you may have written psi t is equal to summation over n from 1 to infinity, n e to the power minus I n t by h car. It is in normal Schrodinger picture. It is in normal Schrodinger picture, SP. And in interaction picture, the essential difference is psi t is equal to n equal to from 1 to infinity. This an will be time dependent. There an should be static, but here an is time dependent of n e to the power minus I en t by h. This portion is identical, but only difference in the Schrodinger picture and the interaction picture is that. Okay. Okay. Now you can use this wave function, this form of wave function in interaction picture in the Schrodinger equation. So I have written the original Schrodinger equation, I h car del psi by del t is equal to ht of psi. Okay. So I h car del psi by del t, right? So del psi by del t means summation over n is from 1 to infinity. Okay, from 1 to infinity. First derivative of this portion, derivative of this portion only. So it will yield n dot of n e to the power minus I n t by h cut, okay, minus I n by h cut of n of d of n e to the power minus I n t by h cut, okay, equals to h of t. H of t means h naught plus lambda of h prime of psi. Psi means summation over n from 1 to infinity. Okay, this is an of t n e to the power minus I n t by h. Okay. Okay. Now h naught operated over n, it will yield en naught. This is en. So en naught e to the power minus I n t by h cut, and here h cut and h cut it will yield the same thing. So this one will cancel out. Okay. So the rest of the equation you have I h cut summation over n is from 1 to infinity, this is n dot n e to the power minus I n t by h cut of n. This is equals to lambda of h prime, summation over n from 1 to infinity, n of e to the power minus I n t by h cut. Okay, this one. Okay, now I am going to use the bra of m. Okay, that means I h cut summation over n dot mn e to the power minus I n t by h cut, okay, of okay, equals to lambda summation over n from 1 to infinity an now m h prime of n e to the power minus I n t by h cut. Okay, so in more general sense, you can write I h cut, okay, summation over n. Okay, I have to try it from some 2 steps before. No. Some 2 steps before, I h cut of n dot of n e to the power minus I n t by h cut, right, equals to, here you can use the different index because this is dummy index, this n is repeating. So as it is repeating, that means this this is dummy index. So you can write in other index also. Suppose lambda, this is m, okay, h prime of am of m e to the power minus I em t by h car. You can write, you can use the other index also. Okay, you can use other index. Now you can use the bra of n in the both side. Bra of n in the both side, and in this case, n and n, bra of n, ket of n, it will yield 1. Okay, so that means, or you can use other different index also. Suppose I am suppose L, the bra of L is hitting at the both end of the equation. So it will essentially yield IH cut of summation over n an dot L and n, okay, e to the power minus I en e by h cut equals to lambda summation over m sorry L h prime of m am e to the power minus I em t by h cut, okay, this one you can write this one now, and this term is equal to Kronecker delta ln, and in this summation only one non-zero term is when L equals to n. So here you can write IH cut of L dot into e to the power minus I EL t by h cut. You have to put L in the place of n equals to lambda. What is this? This one is the matrix element of H prime. So H prime of Lm, okay, H prime of Lm into Am all over summation over m. So m into e to the power minus I em t by h cut, and at last you can write IH cut L dot equals to lambda summation over m e to the power I by h cut EL minus em into t, okay, into am of t. So this is the Schrodinger equation in interaction picture in terms of the orthonormal basis. So this is more simplified form of the Schrodinger equation. In the previous one, you have written it in the form of psi tilde t. So psi tilde t is itself an undefined quantity unless you can split this psi tilde t. Okay, you have already splitted this psi tilde t as summation over m am of t of m. So after putting this clarification for psi tilde t, you have found the Schrodinger equation in that. Okay, so এই হচ্ছে Schrodinger equation in interaction picture. আচ্ছা বলো, এই অবধি তোমাদের কোনো কোশ্চেন থাকলে বলো, তারপর আমরা নেক্সট পোরশনে যাব। কোনো কোশ্চেন থাকলে বলো। কোনো কোশ্চেন আছে? হ্যালো, না স্যার, না স্যার। তাহলে Schrodinger ইকুয়েশনটা আমরা জাস্ট ডিরাইভ করলাম, ঠিক আছে? তো আজকে আমরা এর একটা অ্যাপ্লিকেশন দেখ। ওকে, সো try to apply this idea of interaction picture for some system. So suppose we have an authentic example of instantaneous perturbation. Instantaneous perturbation. Okay. So let consider a two-level system with Hamiltonian initial Hamiltonian is not is equal to suppose this is E1 0 0 E2. So it's a two-level system having energy levels E1 and E2. The corresponding eigenstate should be 1 0 and this is or 0 1. Okay. So this is the uh, original unperturbed system, which is basically two-level system. Okay. Now we are going to perturb this system by the perturbing Hamiltonian, which is time dependent, of course, which is suppose 0 alpha alpha star 0 and Dirac delta of t. So the instantaneous perturbation can be described through some Dirac delta potential, Dirac delta function, because you know delta of t is equal to infinite when t is equal to 0, equal to 0 when t not equals to 0. So at t equals to 0, okay, at t equals to 0, there is a infinitely high peak or infinite pulse which will stimulate the system very instantly. So thus it is the instantaneous perturbation. Okay, so this is the instantaneous perturbation. So now the whole Hamiltonian is now h of lambda t, which is h naught plus lambda of h prime. Now try to describe this perturbing situation in a time graph or in a time scale. Suppose this is time axis and this is t equal to 0. So there is a Dirac delta pulse at t equal to 0. Dirac delta pulse at t equal to 0. So before t equal to 0, the system has the Hamiltonian is not, and after the Dirac pulse is gone, the system has the Hamiltonian is not. But essentially at t equal to 0, in a very instant time interval, the system will possess this Hamiltonian h of lambda t, which is time dependent. The system is essentially time dependent when uh, the perturbation is on, and the perturbation is on for a very short period of time. That means you can say it is short-lived, very short-lived. That means at the interval t tends to 0, and the perturbation is very high but very short-lived. So thus we have used the Dirac delta function to describe the perturbing habit. Okay, so this one. Now try to describe the system. Okay, at t equals to 0, it is a two-level system. It is a two-level system. Initially, there are two levels, one having energy U1 and another is suppose energy E2. Okay, and suppose E2 greater than U1, and the difference is E2 minus E1, the delta E, difference of energies between the two levels. And suppose initially, that means at t less than 0, the particle is in the ground state, which is U1 state. So that means the initial wave function, I suppose, this is suppose psi 1, or you can write in a very Okay, this is 1. The system is completely in the E1 energy level. Okay. Now at t equal to 0, there is a storm blown in the system, blown over the system. There is a very infinitely high peak blow is on the system, and due to this storm, the system will make the transition. Okay, and the system will make the transition from initial state to final state, and there will be some probability to possess the both the energy levels. So suppose you can write F is equal to say it is A1 of 1 plus A2 of 2, where generally A1 is the a mod of A1 square is the probability to be in the ground state, that means in U1 state, and mod of A2 square is essentially the probability to be in the E2 state. Okay, so after t equal to t greater than 0, that means at t greater than 0, p of 1 is equal to mod of A1 square, and p of 2 is equal to mod of A2 square. Now t less than 0, p1 is 1 and p2 was 0, because before the perturbation the system was completely in the ground state. So thus before the perturbation p1 is 1, completely in the ground state, and p2 is 0, and after the perturbation it will make the transition, and there is a probability to be in the ground state, which is mod of A1 square, and p2 is mod of A2 square. And you know, for normalization, mod of A1 square plus mod of A2 square should be 1. Okay. Now following the interaction picture, you have to make this probability coefficient, that means A1 and A2, this should be written as the function of time. So you can write this is A1 of t. So A1 of t is 1 for t less than 0, and is equal to A1 for t greater than 0. A2 of t is equal to 0 for t less than 0, and is equal to A2 for t greater than 0. So thus you can predict this A1 and A2. This A1 and A2 is completely function of time, and the degree of transition, that means how much it will make transition from 1 to 2, it will completely depend on the strength of the perturbation, depend on the lambda, depend on the Dirac delta function property, all of these. Okay, so this A1 and A2 has the time dependence. Okay. Initially it may be in 0 and 1, but after the perturbation it will make transition to a final state. So thus you can in general you can say this A1 and A2 to be time dependent to follow that interaction picture. Okay. Now following the interaction picture, already we have derived the expression of Schrodinger equation in terms of the orthonormal basis. You can use the you can use the Schrodinger equation in interaction picture, which is IH cut of L dot is equal to lambda summation over m e to the power I EL minus EM E by H cut of H prime of LM, H prime of LM of M. Okay. Now here L and M both have the two indices 1 and 2. So you can write, suppose I cut of A1 dot equals to lambda, only the non-diagonal, off-diagonal terms are there in the perturbing Hamilton. So only you have alpha and alpha star. So you can write e to the power I E2 minus, sorry, E1 minus E2, E by H cut, H prime LM, that means this is alpha and this is A2. Okay. So let this one, suppose E1 minus E2, that means E2 is greater than E1. So E2 minus E1 by H cut is suppose omega. Okay. So in general, you can write IH cut A1 dot equals to lambda e to the power minus I omega t, because E2 minus E1 is omega, so this is E1 minus E2, so minus I omega t alpha of A2. Okay, alpha of A2. Sorry, we have missed the Dirac delta function, so that should be delta of t. So alpha delta of t. Similarly, for the second one, you can write IH cut A2 dot is equal to lambda alpha star, okay, lambda alpha star e to the power I omega t, e to the power I omega t, A1t of delta t, A1t of delta t. So now we have the two governing equation. IH cut A1 dot, this is A1 dot, A1 dot is equal to lambda e to the power minus I omega t alpha star delta t of A2, and IH cut A2 dot is equal to lambda e to the power I omega t alpha, sorry, this was alpha, alpha star delta t of A1. Okay, this one. Um, Now, can you write this Dirac delta function to be 0 at t equal to, sorry, Dirac delta function to be infinity at t equal to 0? So, if you put it at t equal to 0, at t equal to 0, A2 is 0. Okay. So, can you write this one in that way? Suppose, can you write IH cut A1 dot is equal to 0, and IH cut A2 dot is equal to lambda to the power I omega t alpha star of A1 is equal to 1. Can you write these two equation? আচ্ছা, এই দুটো ইকুয়েশন কি আমরা লিখতে পারি? একটু রেসপন্ড করবে। এখান থেকে কি এই দুটো জিনিস লিখতে পারি আমরা? Can we write these two equations? লিখতে কি পারি এটা? কারণ A1 এর আর A1 আর A2 ভ্যালুটা বসিয়ে দিচ্ছি। কি হলো? এটা কি আমরা লিখতে পারবো এখানে? মানে A1 A2 ভ্যালু কি এখানে বসাতে পারবো? হ্যালো,
হ্যাঁ স্যার।
না, এটা আমরা এখানে বসাতে পারবো। ঠিক আছে, সো the value of A1 and A2 are not defined. The value of A1 is 1 for t less than 0 only, but after the perturbation we don't know the value of A1. It is function of time. Okay, it will be the function of time. A2 also, A2 is 0 before the perturbation, after the perturbation it will be function of time. Okay, so in general we can write this equation. So here we have to regularize the Dirac delta function. So you know the property of Dirac delta function. Dirac delta function delta t is equal to 0 for t not equals to 0 and equals to 1, sorry, and equals to infinite for t equals to 0. And another property of Dirac delta function, the area of Dirac delta function is 1. Delta t dt is equal to 1. So can we write, so suppose this is time scale, so this is a infinite peak, right? Dirac delta function is essentially a very thin infinite peak at t equal to 0. But you can regularize it. Suppose I am taking it as a rectangular bump like that. It's a rectangular bump. This is t equal to 0 and this is t equal to t naught and this height is 1 by t naught. Thus, you can write this Dirac delta function delta of t is equal to limit t naught tends to 0 1 by t naught. Okay, and it essentially will yield the area to be 1. T naught and 1 by t naught to be 1, and whenever t naught tends to 0 it will be infinite. Okay, so the Dirac delta function, you can write the Dirac delta function in that way. Delta of t is equal to limit t naught tends to 0 1 by t. Now essentially those two equations, I is cut a1 dot is equal to lambda at as t tends to t naught, which is t naught tends to 0, it will essentially 1, and Dirac delta will be 1 by t naught. Okay, and a2 will be the function of time. So lambda alpha 1 by t naught, lambda alpha 1 by t naught. Okay, lambda alpha 1 by t naught a2. Similarly, the second one, I is cut a2 dot, which will yield lambda alpha star 1 by t naught of a1. Okay, so now these are the two equations. These are the two equations, and you can solve these two equations in very easy way. Make the derivative on the both sides of the above equation. So I is cut a1 double dot, okay, equals to lambda alpha 1 by t naught 1 by t naught of a2 dot. Okay, a2 dot. And what is a2 dot? A2 dot is equal to lambda alpha star by I is cut, which is equal to lambda alpha 1 by t dot into lambda alpha star by t naught, which is I is cut, okay, I is cut and a1. Okay, of a1. So essentially you have a1 double dot, sorry, a1 double dot is equal to lambda square mod of alpha square by t naught square, okay, minus of uh, t naught square h cut square of a1. Okay, So this one is suppose omega square. So you have a1 double dot plus of omega square a1 equals to 0, which have the solution a1 equals to a cos omega t plus e sin omega t. Okay. And what should be a2? What should be a2? A2 is IH cut by lambda, IH cut T naught. A2 is IH cut by lambda alpha. IH cut by lambda alpha and T naught, of course, E naught A1 dot. So which is IH cut T naught by lambda alpha, and A1 dot means omega. It is omega 6 P cos omega t minus A sin omega t. Now you have the boundary condition at t equal to 0, A2 was 0, so you can put at t b, then it will find that b should be 0. You can put A2 equal to 0 and t equal to 0, essentially you will find b equals to 0. That means A2 equals to minus IH cut T naught omega minus IH cut T naught omega by lambda alpha of A sin omega t. Okay. And A1 at t equal to 0, okay, at t equal to 0, A1 was 1. That means A equals to 1. Right? A equals to 1. So thus you can write this is A1 equal to cos omega t. And A is 1, so thus A should be taken as 1. Okay. So now you have the solution for A1 and A2. Thus you have the complete solution F is equal to A1 of 1 plus A2 of 2. Okay. So clearly the picture is, this is suppose t equal to 0. Before t equal to 0, the system is I, which is completely at one state, and there is a perturbation, instantaneous perturbation at t equal to 0. And this perturbation, or you can think of it as a storm, the storm will change the life of this system, and the system will be changed up to the final state, which is suppose A1 of 1 plus A2 of 2, and you will find this A1 and A2 to be sin theta and cos theta. Okay, A1 to be sin theta and cos theta, that is sin omega t and cos omega t. So this A1 and A2 are harmonic. So harmonically, whenever you put some Dirac delta function to the system, Dirac delta pulse to the system will periodically transit from one state to two state. Okay, you can realize it in the picture. This is two state and this is one state. Suppose at t equal to 0, the system is completely here, and with the time, whenever you have applied some Dirac delta pulse on the system, with the time, the probability to be stay in here, the probability of occupation in the first state, it will decrease, and here it will increase. After that, after a complete cycle, again the system will grow here and it will decay here. Okay, so due to instantaneous perturbation, that means due to the allowance of